So today we want to start with chapter 5. And in this chapter, I have divided into two parts. So for this first part, we are going to learn how to standardize a variable. You're also going to be able to tell what happens to the location parameters or what happens to the scale parameters when distributions are shifted or scaled. We're also going to talk about the normal distribution and then answer some problems on them and also talk about the 68, 95, 99.7 rule. And then we'll practice a couple of problems. So what do we mean by to standardize a variable? So to standardize a variable, what we mean is that we subtract the mean and then we divide the difference by the standard deviation. So when we talk about standardizing a variable, we mean doing this. This y bar here is the mean of the variable. And then the S is the standard deviation. So whenever we do this, we have standardized the values. And we are going to look at the importance of standardizing variables. It's going to help us to compare stuffs. We'll get into that as we proceed. And whenever we do this, we usually call this the z-scores. StatCrunch can do this for you, or you can also use Excel and stuff to do this. But it's very important that you're also able to interpret the meaning or the output. So whenever you have a z-score of 1, what it means is that the data value is 1 standard deviations above the mean. You see this one here is positive. Is that okay? That is why it's above the mean. And then one thing you also have to know is that the z-scores, they don't have units because we have standardized them. And also data values that are below the mean have negative z-scores. So for example, you see this one means that this z-score is what? 1.1 standard deviations below the mean. Is that okay? And then you should also know that a data value that is far from the mean usually has an unusual z-score. Any questions so far? Okay, now I've spoken about z-scores and why and also how to standardize variables. Now, the question is, why do we need this? Is that okay? And so I have an example to explain why or the importance of using z-scores. Let's look at this example here. It says that imagine two friends, Alice and Bob, participate in two different races. So these are two people, and then they participated in two different races, right? And then you want to figure out who performed better relative to their races. That is what you want to do. Two people, they didn't participate in the same race. They participated in different races. And then you want to figure out who performed better relative to their races. Now, these are the data. For Alice, Alice runs 5 kilometers in 25 minutes. Or you could put miles, it doesn't matter. 5 kilometers in 25 minutes. And then the average time for the 5 kilometers is 28 minutes. And then the standard deviation for the 5 kilometers is 2 minutes. And then Bob, he ran 10 kilometers in 55 minutes. And then the average is 60 minutes. And then the standard deviation is 4 minutes. Now, how can you answer who performed better relative to their races? Anybody has an idea? Who do you think, when you have this information, who do you think performed better? Look at the time they used to run, look at the average, look at the time they used to run, and look at the average. What can you say? Why do you think Bob did better? Okay. Anybody else? So who do you think did better? Bob. I see. Anybody else? Mm-hmm.
Better because she did 1.5 times the standard deviation, whereas Bob did 1.3 times.
Okay. Great. So to be able to answer questions like this, you realize that because they are all in different races, we are going to use the z-score to be able to what? Compare. Is that okay? So this is the importance of what? Understanding z-scores. Is that okay? So let's try to use the z-scores to be able to answer our problem. We want to know who performed better relative to their races. So now that we have the z-score formula, I want you, this is the z-score formula. Compute the z-score for Alice and compute the z-score for Bob. Does that make sense? This is the z-score formula. And then we have this information here. So compute the z-scores for Alice and compute the z-scores for Bob. So when we do that, this is the z-score formula here. And remember, you were given the average and then a standard deviation for each of them. You see the mean for Alice, standard deviation for Alice. Mean for Bob, standard deviation for Bob. So then applying that, you can see the z-score for Alice is negative 1.5. And then the z-score for Bob is negative 1.25. Now we have the z-scores, right? Because it is races, because they were running and the z-scores are negative, it means that they performed better than the average. Does that make sense? Right? Because if the average run time is 25 and their z-score is negative, it means that they finished earlier than the average, right? So that is one thing we can see here. So you see, you are trying to interpret the z-score based on the problem at hand. And so when we have these two, we can see that Ali's z-score means that she finished the 5 kilometers race 1.5 standard deviation faster than the average runner, isn't it? And then Bob's z-score was negative 1.25, which also means that he finished the 10 kilometers race 1.25 faster than the average runner. So you can see that looking at this, because Alice only is 1.5, we can conclude that what Alice performed better relative to her group than Bob did. Does that make sense? Any questions? So now you see the importance of the z-score. Is that okay? It has helped us to be able to make this judgment. Okay. So you see, without a z-score, it will be very difficult. We only know their raw times, and it'll be very difficult to be able to make direct comparison. So because they are in different races, and so they are not directly comparable. So the z-score standardized their performances, allowing a fair comparison. So you see, z-scores helped us to answer questions like who performed relative better to their peers, or how far above or below average was their performance. So the z-score, in summary, is a tool that helps us to compare results across different skills or contests. Is that okay? Good. You could also apply the z-scores to compute grades. So if you want to like how somebody performed in math with history, there are two different subjects. But if you have the mean, the standard deviation, you can be able to tell how they did better compared to those in those groups. Does that make sense? Okay. So the next thing we want to do, now we've been able to understand these two things, that for finding z-score, we first subtract the mean and then we divide by the standard deviation. Is that okay? Now we want to learn and answer problems. We've already learned about location parameters. We've already learned about scale parameters. And so we want to be able to analyze what happens to the measures of location and spread when we add or subtract a constant. And so in view of that, go to As You Learn and then go to week 3 and then open this Excel file. As You Learn week 3, you see this Excel file there. Okay. I want us to be able to write this problem down. What happens to location when we subtract or add? Because I would open the Excel file, and so we should be able to, so when you go to the Excel file, then we'll be able to answer this problem. What happens to the location when we add or subtract? What happens to the spread when we add or subtract? And also what happens to the location when we multiply or divide? And then also what happens to the spread when we multiply or divide? So please write these questions down. So this is going to help us to answer questions about shifting and then scaling. Is that okay? So do you have this Excel file? Okay. So I'm going to explain what's in this Excel file. So now when we look at this column here, it's just telling you you have sample data points. Is that okay? And then this is the mean of this data, the median, the minimum, and then the maximum. Is that okay? And then for spread, measures of spread, this is the standard deviation, and then this is the interquartile range, and then this is the range. Is that okay? Does that make sense? So for this data set, this is the mean, median, minimum, maximum. These numbers are measures of what? Location. And then for spread, we have the standard deviation, interquartile range, and the range. Okay. So now we want to answer, when we talk about shifting, shifting means adding and subtracting a constant from your data set. Is that okay? So you can see, you see this original data here, when we come here, we try to what? Shift it by adding 20. So you see 10 plus 20 gives you 30. Is that okay? 20 plus 20 gives you 40. So all the data points here, we have been able to what? Add 20 to it. Is that okay? Does that make sense? Now, look on top. What do you see? What has happened to the measures of location? So these are the measures of location. Compare this one to this one. What can you see? So you can see that they have increased by 20. Do you all agree with that? So what happens to the measures of location? Have they changed or they have not changed? So the measures of location changed when we what? We shifted. Is that okay? So adding 20 means we have what? Shifted. Does that make sense? Okay. So what happens to the measures of spread? It stays the same. Does that make sense? So you see that when we add or subtract a constant, what in summary, what can you say happens to the location? We can say that location changes, but the spread does not change. Are we all clear on that? Okay. Now let's come to scaling. So this is this same data set here. Scaling is multiplied by a constant or dividing, the same thing. So you can see here, all we did was to multiply everything here by 10. What happens to the measures of location? You can see the locations have also what? Changed, right? Look at the location. It used to be 50, now 500. It used to be 10, now 100. It used to be 200, now 2000. What has also happened to the spread? It used to be 57.6, now 576.87. 40, now 400. 190, now 1900. So you can see that when we multiply by a constant, both location and scale changes. Does that make sense? When we multiply by a constant, both location and scale changes. Now let's come here too. We can see this same thing here. We divided by a constant. We divided everything here by 2. So we get this. What happens to the locations? You can see we compare the original to the new one. It has changed, right? And then you can see that the measures of spread, which is the standard deviation, IQR, and range, has also changed. Okay, now let's do what happens to both when we multiply the original by 100 and then we also shift it by adding 5. So we multiply everything here by 100 and then we add 5 to it. That is what this row here means. So here, this row means that we shifted and scaled. Is that okay? We shifted by adding positive 5. We scaled by multiplying by 100. Now, what happens to measures of location and then scale? We compare to this, so you can see measures of location has changed, right? You can also see that the measures of spread has also changed. Any questions so far? Okay, now that we know this, let's get to our slides and then put in what we have learned there. So now let's answer, what happens to location when we add or subtract? Does it change or doesn't change? Everybody, what happens to location when we add or subtract? Changes, good. What happens to spread when we add or subtract? Good. What happens to location when we multiply or divide? Do you all agree it changes? Good. What happens to spread when we multiply or divide? Good. Now I want to ask you, what happens to location when we multiply and and also add? Changes, right? Okay. So this is the answer we summarized here. The next thing we want to talk about is the 6899.7 rule. So this was initiated by a man called De Moivre. So what he's saying is that whenever you have a symmetric distribution, we've already talked about symmetric distribution, which means that they are bell-shaped, right? And then a perfect example is a normal distribution. So what he is saying is that it means that 68% of the data values fall within one standard deviation of the mean. What it means is that if you have the mean plus or minus standard deviation, it means that what? 68% of the value fall within this range. Is that okay? And then 95% fall within two standard deviations. So whenever we have this, it means that this range will be, so for two standard deviation, right. So it's saying that 95% of the observations fall within this range. And then 99.7 fall within fall within three standard deviations of the mean. So this blue curve here is an example of a symmetric distribution. You can see it is what? Bell shaped. And so this is what? One standard deviation of the mean. So here you can see that the mean is what? 0. Remember, the mean is the what? The center. Is that okay? So you can see here that the mean is 0. And so here is 34% plus 34%. That is what? 68%. Does that make sense? To two standard deviations, we are talking about this range. And then three standard deviations, we are talking about here. So that is what the 68, 95, 99.7 rule is saying. Any questions on that? Okay, let's proceed. Now, we want to learn how to use StatCrunch to answer problems from symmetric distributions or from the normal distribution. So to do that, I want you to know that, let's read the problem. It's saying that SAT math has, so when you see this n here, it means that it is normally distributed. Is that okay? And then the first number you have here is the mean. Does that make sense? And then this is the what? Standard deviation. Does that make sense? So this first number you have here is the mean, and then this is the standard deviation. And then we want to be able to use StatCrunch to answer what percent of students score is less than 600, greater than 700, and what have you. So what I want you to do is open StatCrunch, go to Stats, Calculators, and then you click on Normal. So let's try to do that. So you see, we have StatCrunch here. And then let's go to Stats. And then let's get to Calculators. And then let's scroll down to Normal. I repeat again, we go to Stats, Calculators, and let's scroll to Normal. Let's hit on this one here. Now let's put in the mean. Our mean is what? What was our mean? 500. Our standard deviation was 100. And then let's compute what percent of score is less than 600. Let's put 600 here. Then let's hit compute. Do we see that? So whenever you have this, the first thing you have to do is to put in the mean and then the standard deviation. Is that okay? So when we put in the mean and then the standard deviation, then we are able to answer our question. The first question is that what percent of students score less than 600? So you can see X less than 600 here. That is what? 84.13%. We can see that. Now, how do you do greater than 700? B. B says that greater than 700. With the same mean and standard deviation, all we need to do is to change. We just click on this one and then change it to greater than. Does that make sense? And then we change this 600 to 700. Right. And then we hit compute. You see, whilst it's computing, it's also shading for you the region. And then the C is saying is what the C says that between 200 and 400. Between 200 and 400. So to do that, you see, let's go and click the between. Look at where the between is. Let's go click the between. We click on that and then 200 and 400. Do we see that? And then we hit compute. So you see it has shaded. If you look at where 200, look at where 400 is. You see, it is that range. And then it has computed for you. For this course, you don't need to, usually in some advanced stat course, we use normal table where you have to read. For this, StatCrunch does it for you. Is that okay? So you should be able to know how to use StatCrunch to get your answer and also how to be able to interpret that. And then the last one we want to do is to compute the 95th percentile. To be able to do that, let's get back to our standard. Are we all there? When we get to standard, let's change the greater than to less than. So to compute, it doesn't only have to be the 95th percentile. It could be 80th percentile, whatever percentile is it. You have to come to standard. Is that okay? When we come to standard, here has to be less than. Is that okay? And then we put in 0.95 here. And then we hit compute. So you see, it has given us 664.485. I go over how to compute the percentile again. So to compute percentile, we come to standard, we hit the standard, right? And then we make sure that here is what? Less than. And then we leave here blank. And then we come and put the percentile here. Is that okay? Look at, I didn't put the 9.95 here. I placed it here. Is that okay? That is how to use the StatCrunch to compute the 95th percentile. When you do that, you hit compute, then it fills here for you. So that is the 95th percentile of the SAT math distribution. Now, do you have any questions on this? Okay, now I am coming to put a problem on the board and then you spend time, use StatCrunch to answer them. And I'll be calling you for you to share what you got with me. Is that okay? Okay, let's do that. So I want you to answer this problem. Don't look at the solutions I've provided. Try to do them by yourself. That way, if you don't understand anything, you could ask and then you would understand them. Is that okay? Because you'll be doing homework problems on this, you do exams on this. So make sure that you know how to do them. Right. So now read this problem and then answer A, B, C, D. So when you read the problem, we've been told that we should assume that a normal model is appropriate for the distribution of the driving times. That is what we've been told here. Is that okay? And so we go to stat, calculators, and then we head to the normal. So when we head to the normal, who will tell us what mean and standard deviation should we use? So he's saying 20 and 2. How many of you agree with him? Okay, good. So let's put our 20 and 2 there. Do you all agree with that? Okay. The question is saying, how often will you arrive at school in less than 22 minutes? How do we do that? Anybody? Okay. Do you all agree with her? Okay, good. So let's do that. And then we hit compute. Right. Okay. How about B? How do we get that? Okay, so we flip the sign and put this here to be 24. Right? Do you all agree with this? Okay, how about C? So for C, StatCrunch cannot help us do that. Is that okay? Because C, it's more about intuition. Is that okay? So what does a symmetric distribution means? It means that it is what? Bell-shaped. So do you think that your driving times is symmetric?
Yes. So therefore symmetric.
Okay, good. Anybody else? I saw your hand. Do you want to say something? Anybody wants? Do you want to say something? Okay. Anybody wants to say something? Okay.
So
Mm-hmm.
is there like a better way of like determining it? You just go based off of like you said, your intuition.
Yeah. So this C for the A and B, we are strict. They told us to use the normal model. Is that okay?
Yeah.
For C, they are asking you. So it's like, though they have restricted, they are trying to ask you, do you think your driving times is symmetric? That means, do you think it's like bell-shaped? So I don't think it's symmetric because we know that sometimes there could be days that we could be impacted by heavy traffic. And so you are going to arrive very late. Do you agree with that? So let's say you live in Illinois and then you drive to Boone every day. Most of the times you might be arriving like 45 minutes, right? Which it's symmetric. But there are some days like you could have snow that that will impact your arrival time. There could be days that there could be traffic. So in those days, you see that the arrival time is maybe if it's 45 minutes, those will be like 1 hour 30 minutes. It's very far from the rest, which is going to make the distribution skewed to the right. Does that make sense?
On the test or something, would we have a like an answer?
Yeah, so like C, you have to write what you think. Does that make sense?
But is there like a concrete way of finding what's right versus what's wrong in that answer, or are we just basically guessing? Is it
So this one, there is no concrete way of saying like maybe answer it this way. So this is trying to ask you in relative. So what they're trying to ask you is that, do you understand what symmetric distribution means? Does that make sense?
Yeah.
So when you realize that, well, I drive to school, but it's not going to be every day, right? What is skew distributions? It's just that there could be some days that it's going to be, you are going to have maybe symmetric means that every day is like this. There are days that it's your arrival time will be here, and then you see because of this guy, it's going to make everything here, and then you see it's not symmetric.
Right.
So you just need 1 or 2 days that your time could be way off. Does that make sense?
I gotcha. I wrote unimodal, but
So that is what it means. So you just have to think about it like live in Illinois. Well, every day when you use the Google, it takes like 45 minutes to get to Boone. Yeah, that could be true. But you remember some days you have snowstorms and stuff. So if you don't clear the road early, you're going to spend like 1 or 30 minutes to get here. And there are days there could be traffic. stuffs could happen. Is that okay? Not based on your doing, but natural events, right? And so even if you have 4 or 5 of them, it's going to change everything. Is that okay? Just like one Elon Musk in this classroom, his income is going to make everything heavily skewed. Just one person. Is that okay? Good. And so when it's skewed, it means that we shouldn't use a normal model to do it, and so it's going to impact our predictions. That's what it means. Is that okay? But for now, when they want you to use the normal, they'll tell you use the normal, and then we go by StatCrunch. But for C is just trying to ask you about your intuition, and that's all. Any questions on this?
No.
Okay, good. And so make sure that you do your homework. We'll be having a test coming up soon. So make sure that you understand all that we're doing. Is that okay? Good. I think that should be all for today. I'll see you